Giant steel wire ropes, forged through precision manufacturing, power-heavy lifting, offshore rigs, and industrial giants, showcasing strength, safety, and innovation. The production of a large-diameter wire rope sling with a soft-eye splice is carried out on-site using a mechanical splicing system. First, the ferrule is positioned correctly, and the wire rope is inserted. The Talurit RBS machine then assists the bending process, ensuring precise alignment and controlled formation of the sling eye. Next, the eye formation is mechanically assisted to achieve the required loop size. Swagging is then performed, compressing the ferrule securely around the rope strands to guarantee strength and durability. Finally, the soft-eye wire rope sling is completed, ready for heavy lifting applications. In May 2013, the Hendrik Vader Group achieved a remarkable milestone by producing 2 cable-laid slings, each measuring an impressive 280 meters in length. These are recognized as the world's longest cable-laid slings ever manufactured. Weighing 63 metric tons each, the slings were carefully terminated with 2 hand-spliced soft eyes, ensuring both strength and reliability. Their massive scale and precision craftsmanship made them suitable for the most demanding offshore tasks. Commissioned by Saipem, the slings were deployed in subsea field installation at the Asgard field in the Norwegian Sea, highlighting excellence in engineering and rope technology. The Hendrik Vader Group is a leading European specialist in steel wire and fiber ropes, serving mainly the offshore and maritime industries from its strategic bases in Rotterdam, Aberdeen, and Stavanger. These locations, at the heart of Europe's energy capitals, position the company close to its customers and their demanding projects, whether lifting, towing, or mooring. With a proud heritage dating back to 1545, the group has evolved alongside technological progress and market needs. From traditional manila ropes to advanced materials such as polyester, Dyneema, and steel, Hendrik Vader combines centuries of expertise with modern innovation. Today, the company designs and manufactures high-performance wire rope slings, grommet slings, and related lifting and towing equipment for some of the toughest tasks in the industry. Its operations include proof load and breaking load tests of up to 250 tons, ensuring the reliability and safety of its products. Services extend further with spooling, reeving, inspections, and certification. To meet urgent needs, the group also maintains more than 3,000 stock items in warehouses across Europe, backed by a global supplier network. Hendrik Vader Group is ISO certified and trusted by industry leaders for its expertise, resourcefulness, and commitment to quality. Its achievements include producing the world's longest 280-meter cable-laid sling, a symbol of its ambition and technical excellence. The production of wire sling ropes is a carefully organized sequence of steps that transforms raw wire rope into strong and reliable lifting tools. To achieve this, both machine-assisted mechanical splicing and traditional hand splicing methods can be used. However, in mass production, mechanical splicing dominates because it allows for greater efficiency, consistency, and output. By following a clear progression of operations, manufacturers are able to ensure that every sling rope meets demanding industrial standards. To begin with, the process starts by cutting the wire rope to the required length. Large coils of steel rope are unwound, and specialized hydraulic cutters are used to make precise cuts. This stage is crucial because an accurate length ensures that the finished sling rope matches the customer's specifications. At the same time, clean cuts minimize the risk of fraying and make later steps smoother. Once the rope has been cut, the ends are prepared for splicing. After cutting, the rope is positioned in a splicing machine if mechanical splicing is chosen. At this point, part of the rope end is unraveled, allowing the individual strands to be manipulated. This preparation is necessary because the rope end must be bent back towards the main body to form a loop. This loop, known as the eye, is essential since it provides the attachment point for hooks, shackles, or crane connections. By carefully arranging the rope end, workers set the foundation for a strong and durable splice. Next, the eye is formed by bending the rope end around and placing it alongside the standing part of the rope. A metal sleeve, called a ferrule, is then slipped over both the returning end and the main rope. The ferrule functions as the main connector that will permanently lock the eye in place. Without this step, the rope would not maintain its shape under heavy loads. Once the ferrule is positioned correctly, the rope is ready for swaging. Afterwards, the rope with its ferrule is placed inside a swaging press. This hydraulic machine exerts massive pressure, compressing the ferrule tightly around the rope strands. In most cases, several compressions are applied along the length of the ferrule to ensure an even and secure grip. As the ferrule is pressed, the strands become locked together, preventing any movement or slippage. This stage is one of the most critical because the strength of the finished sling depends heavily on the quality of the swage. Once the swaging is complete, the rope undergoes an initial inspection. At this stage, workers check the size of the eye, the positioning of the ferrule, and the general condition of the rope. If any irregularities are detected, further pressing or trimming is carried out. For instance, small protruding wires may be cut away to give the sling a smooth finish. By carefully inspecting and adjusting, the manufacturing process ensures that only ropes of high quality move forward to completion. Then, once inspection is finished, the mechanical spliced wire sling rope can be considered complete. The rope now has a solid eye loop at one or both ends, making it suitable for a wide variety of lifting applications. Because machines can repeat this process quickly and consistently, mechanical splicing allows factories to produce sling ropes in large quantities with less effort compared to manual labor. As a result, this method has become the standard in industrial mass production. Nevertheless, besides mechanical production, sling ropes can also be made by hand. In this traditional method, the process begins the same way. the rope is cut to the required length, and the strands are carefully unraveled. However, instead of inserting a ferrule, the rope end is bent back to form an eye, and the individual strands are tucked back into the main body by hand. Next, the craftsman weaves each strand over and under the standing strands in a repeating sequence. This interlacing creates a natural lock that holds the loop firmly. The tucking process is repeated several times to build strength and prevent the splice from loosening. Once all strands are secured, the splice is tightened with tools such as marlin spikes or hammers. Afterwards, the rope is smoothed and compacted. Excess wire ends are trimmed away, and the eye loop is checked for uniformity. Although time-consuming, hand splicing produces strong sling ropes and demonstrates the skill of traditional rope making. However, because of its slower pace, it is mainly used for small quantities, custom lengths, or repair work rather than mass production. Finally, regardless of whether the sling rope was made by machine or by hand, the last stage is quality control. Visual inspections are carried out to ensure the eye is properly formed and the splice is secure. In addition, random samples are subjected to load testing. The Hendrik Vader Group has expanded its rental fleet with 12 identical steel lifting slings, each measuring 61 meters in length and 0.36 meters in diameter. The production of these massive slings represents a combination of traditional craftsmanship and advanced machining precision, ensuring that every detail meets the demanding requirements of heavy lifting operations. The process began with thorough engineering, where detailed specifications were drawn up to match the intended application. Once the design phase was complete, the focus shifted to the supply chain. To guarantee consistent quality, the steel wires required for these slings were sourced from Asia. Their delivery was carefully scheduled using a just-in-time approach, allowing the production team to meet tight deadlines while avoiding unnecessary stockpile. After arrival, the wires underwent strict quality checks before being processed. Skilled technicians, supported by advanced machinery, carried out the intricate steps of braiding and forming the slings. Precision was essential at this stage, as the strength and durability of each sling depended on the accuracy of the splicing and mechanical finishing. The integration of handwork with machine-assisted processes created a product Throughout production, continuous monitoring and inspections were conducted to ensure every sling adhered to both internal standards and international safety regulations. The result was a set of 12 robust lifting slings, uniform in size. By successfully completing this project, the Hendrik Vader Group once again demonstrated its expertise in producing high-quality lifting solutions, while also showcasing its ability to coordinate complex supply chains and deliver specialized products on time. The non-contacting wire rope, non-destructive evaluation process ensures safety and reliability without damaging the rope beyond. First, the rope moves continuously through a specially designed rope-moving machine, which allows for smooth and controlled inspection. Next, wires are carefully attached to the rope to establish a connection with the monitoring system. An important feature is the air gap, or liftoff, maintained between the rope and the sensor head, which prevents direct contact and eliminates wear during testing. Finally, the system produces a chart recording, providing detailed data about the rope's internal and external condition, enabling accurate assessment and early detection of defects. During the DNV inspection of a huge Grommet sling in the testing lab, the sling undergoes rigorous evaluation to ensure compliance with safety and quality standards. The process includes visual examination, precise measurement, and load testing under controlled conditions. By simulating real operational stresses, inspectors verify the sling's strength, durability, and reliability. This inspection guarantees that the Grommet sling meets international certification requirements for heavy lifting operations. Inspection and load testing were carried out on an Ingersoll-Rand pneumatic air winch after replacing its wire rope. The process began with the safe removal of the old rope and the installation of a new steel wire rope, properly seated and secured onto the drum. Once the replacement was completed, a detailed inspection of the winch followed, including checking the drum, control valves, and braking system to ensure all components were in good working condition. After verification, the winch was subjected to a controlled load test to confirm its lifting capacity and operational reliability. The load was gradually applied while monitoring the rope tension, drum alignment, and braking response. This test ensured that the winch could safely perform under rated working conditions. The successful inspection and load testing demonstrated the winch's readiness for safe and efficient use in demanding industrial applications. The vertical drop test evaluates offshore containers according to DNV and BSEN 12079. Containers are lifted and dropped from a specified height to verify structural strength, impact resistance, and compliance with international safety and offshore transport standards. A crane load test was conducted in Victoria using Dynamics certified steel test weights. These weights were carefully placed onto a test weight tray and secured with associated rigging gear. The procedure aimed to verify the crane's lifting capacity, stability, and safety under controlled conditions. Such testing ensures compliance with industry standards and provides assurance of reliable performance during future lifting operations. Recently, the lifting of 3 FPSO modules was successfully completed, including the 3 669-ton S-20, the 2 960-ton P-60, and the 2 766-ton P-20. Julie Sling played a vital role by supplying key lifting products such as balanced beams, shackles, and grommet ropes, each with a working load limit of up to 3,000 tons and 2 500 tons. In addition to providing high-performance equipment, Julie Sling also developed a rigorous lifting program to ensure safe and smooth operations. With precise planning and reliable products, The FPSO modules were lifted and positioned efficiently, demonstrating Julie Sling's expertise and strength. The 530-ton boat lift gantry crane underwent heavy load testing at Port Klang, Selangor, Malaysia. Conducted for Destiny Shipbuilding SDNBHD, the test involved lifting 529 tons, ensuring the 430T. At the Aspire Apartments in King Street, Melbourne, Hickory Constructions utilized a 4.5-ton electric hydraulic winch to raise the production deck inside the lift shaft. Delivered by tail crane to level 53, the winch was positioned using jacks and prepared for operation. It is powered by a 3-phase power unit and provides a line pull capacity of 4.5 tons, with 200 meters of rope on the drum. The system includes sheave blocks to guide the rope in 2 parts, ensuring efficient lifting. A key feature is the Archimedes screw, which lays the rope evenly in layers. Additionally, the winch is equipped with an overload protection system that automatically stops operation if the load exceeds its limit, ensuring safe and reliable performance. The SGC 250, also known as Big Carl, is officially recognized as the world's largest ring crane. Designed and built by Sarans, this colossal piece of equipment represents the pinnacle of modern heavy lifting technology. With an unparalleled lifting capacity of up to 5,000 tons, the SGC 250 is engineered to handle the heaviest loads required in large-scale industrial and infrastructure projects. Its remarkable strength and flexibility make it an essential tool for the construction of power plants, refineries, bridges, and offshore facilities. One of the most distinctive features of the SGC 250 is its ring-shaped track system. This innovative design allows the crane to rotate a full 360 degrees while maintaining stability under extreme loads. The crane can be equipped with a main boom up to 160 meters long and a jib extension reaching 100 meters, enabling a maximum hook height of over 250 meters. Such dimensions provide unmatched reach and versatility on site. The SGC 250 is not only powerful, but also highly adaptable. Despite its massive scale, the crane is designed to be dismantled and transported in sections, allowing it to be reassembled at different project locations worldwide. Its modularity ensures efficient mobilization while minimizing downtime. Since its debut, the SGC 250 has been deployed in some of the most challenging and prestigious projects around the globe, most notably at nuclear power plant construction sites. Its ability to lift prefabricated modules weighing thousands of tons has transformed modern construction methods, reducing time, cost, and risk. Ultimately, the SGC 250 stands as a symbol of engineering excellence, combining strength, precision, and innovation to meet the ever-growing demands of heavy lifting in the 21st century. The TCC 7800 is a crawler crane that represents a new benchmark in lifting capacity and versatility for the heavy lifting industry. Designed with cutting-edge engineering and robust structural components, the crane can lift more than 600 tons, making it one of the most powerful machines in its class. This extraordinary capacity allows it to handle the heaviest loads encountered in large-scale construction, petrochemical, shipbuilding, and offshore projects. The crane is equipped with a strong lattice boom system, providing superior reach and flexibility for a wide range of lifting operations. Its advanced hydraulic and electronic control systems ensure smooth, precise, and safe handling of loads, even under the most challenging site conditions. With optimized counterweight configurations and a stable crawler undercarriage, the TCC 7800 delivers outstanding stability and efficiency on uneven terrain, reducing the need for extensive ground preparation. In addition, the crane's modular design enables easier transportation and faster assembly, which significantly reduces downtime on project sites. Safety is also a top priority, with redundant systems, load monitoring technology, and real-time operational feedback integrated into its design. Overall, the TCC 7800 combines sheer lifting power with technological innovation, offering contractors a reliable solution for tackling the most demanding lifting challenges worldwide. It stands as a symbol of engineering excellence in modern crane technology. The production of giant crane slings demonstrates the precision, strength, and craftsmanship required to manufacture these critical lifting components. Giant slings are essential in heavy lifting industries, where they are used for hoisting massive loads such as ships, offshore structures, wind turbine components, and large industrial machinery. The process begins with the selection of premium steel wires, carefully inspected for strength and durability. These wires are then stranded together into robust ropes through specialized machines that ensure uniform twisting and tension. Once the ropes reach the required thickness, they are meticulously shaped into slings according to the design specifications. A vital stage of production is splicing, where the rope ends are skillfully woven back into the body to form secure loops or eyes. This traditional yet highly technical process guarantees maximum safety and load-bearing capacity. The slings may also be reinforced with protective sleeves or coatings to resist abrasion and corrosion in demanding environments. After assembly, each giant sling undergoes strict quality control and load testing. These tests verify that the slings can withstand extreme forces without deformation or failure. The result is a reliable product that ensures safety in the most challenging lifting operations. In conclusion, the creation of giant crane slings is a remarkable combination of engineering, advanced machinery, and skilled labor, reflecting the highest standards of the lifting industry. Yagen. The installation of the giant sling system, capable of lifting more than 24,000 tons, marked a milestone in offshore construction. The process began with the placement of the horizontal top part, followed by the roll-up of the bottom section in row 1. Despite earlier delays and rising costs, the assembly phase was executed with remarkable efficiency. Within just 5 days, all 4 massive modules were installed, each representing a crucial element of the platform's overall structure. The challenge intensified as the project moved offshore, where the modules had to be transformed into a single integrated platform. These 4 modules, once interconnected, formed a colossal structure exceeding 24,000 tons in total weight. To achieve this, vast amounts of steel, pipes, and cables were meticulously joined together, ensuring strength, stability, and functionality, The complexity of this task required precision engineering and close coordination among teams, as every connection played a vital role in the platform's performance. Ultimately, this installation stood out as one of the most significant platform assemblies undertaken within the Equinor system in many years. It highlighted not only the scale of modern offshore projects, but also the capability of advanced sling technology to handle extreme lifting operations.